Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think yesterday we were discuss about the synthetic application of ethyl acetoacetate or acetoacetic ester or ethyl acetoacetate. And as we know that ethyl acetoacetate, it is one of the example of active methylene compound or reactive methylene compound. Why acetoacetic ester or ethyl acetoacetate called as active methylene compound? Because it containing as a active methylene group. CH-2 group is known as active methylene. When? Because there are a number of organic compound which containing as a CH-2 group, but all of them is not called as a active methylene group or the reactive methylene group. The reactive or the active methylene group are those which flanked between two strong electron withdrawing group. Such groups are known as reactive methylene group or the active methylene group, and those compound containing or possessing or having such group are known as active methylene compound or the reactive methylene compound. And so far we have studied near about 7 application. Now is application number 8 which we are going to discuss right now. See here, synthesis of cyclobutane methyl ketone using ethyl acetoacetate or acetoacetic ester or beta keto ester. Now first what you required, first essential requirement to draw the correct structure of the given molecule, given target molecule, or we can say given final product or the given end product, which is given here. Cyclobutane methyl ketone. Remember the structure of cyclobutane methyl ketone is this one. So here CH2, here once again CH2 and this CH2. This is a cyclobutane ring and there is a methyl and ketone means carbonyl group is there, and therefore this is the given target molecule is there, and they had provided us the starting material also, which is ethyl acetoacetate or acetoacetic ester. So first requirement is planning suitably so that you can achieve your end product or the desired product by maintaining suitable reaction condition as well as using proper reagent. So first point is a planning. So planning, in that I am mentioning here as a 2 point. Now look at here, I am making here square bracket. Don't think it is a, I am highlighting this group CH3 C double bond O CH group. It means that this group, this CH C double bond O CH3, this part of this molecule or organic compound, this is coming from, this is coming from acetoacetic ester or ethyl acetoacetate or beta keto ester. Ethyl acetoacetate or acetoacetic ester or beta keto ester. Now second point which I am going to mention over here. Now once again See carefully, I am highlighting this group over here. See, CH2, CH2, CH2 means this CH2, CH2 and CH2. If you see this part also, this part is coming from dihalogen, coming from dihalides, that is X, CH2, CH2, CH2 and X. So 1, 3 dihalide you can say here. And now start the synthesis. Once you do the proper planning, then next point will be the synthesis. Start the synthesis here. Synthesis. In the synthesis part here, this one, the starting material is a ethyl acetoacetate, and you know that the structure of ethyl acetoacetate, CH3, C double bond O, CH2, C double bond O and OET. This will be the structure of ethyl acetoacetate, and this ethyl acetoacetate, the first step, because this is a base catalyzed reaction, and usually we are using the reagent which is NaOET. The chemical name of this reagent is a sodium ethoxide. Sodium ethoxide which will abstract the highly acidic proton which containing as a methylene group normally, and therefore you will get CH3, C double bond O, CH minus charge, then C double bond O, OET. The organic species which carries negative charge, that species are generally termed as carbanions, and that carbanion is well stabilized in this particular case is due to the resonance effect or the mesomeric effect. Then you can write here CH3, C double bond O, CH minus C double bond O, OET, and it will be treated with appropriate dihalides. I am taking here Br, CH2, CH2, CH2 and Br. Now this negative charge is going to attack on this carbon atom. There will be a nucleophilic substitution reaction occurs, and you will get here CH3, C double bond O, then CH. I am writing here CH2, CH2 and one CH2 and Br like this, C double bond O and OET. And once you get this intermediate, what is the next point? Next point will be whether, now is a question arises whether the first one is a alkylation or hydrolysis. Remember, if there is a monoalkylation then followed by hydrolysis process which produce the acid, and that acid further treated with, just heat it, there is a evolution of carbon dioxide and resulting compound obtained will be negative charge, and that negative charge or that carbanion will pick up the proton from water during workup process, and finally you will get the desired product or the final product. But here During the dialkylation, remember for monoalkylation we do the general step by step, but in case of the dialkylation, remember after using the first base and first this process is alkylation, and now further you treat with the another molecule of the base. Remember, don't do the hydrolysis first. If you do the hydrolysis first, what will happen? There is a reason behind it, why I am not hydrolyzing, why I am using sodium ethoxide rather than hydrolysis. The reason behind it is that if I did hydrolysis here, the hydrolysis is a process which convert ester into as acid. Once acid is formed, and then if you use as any base will pick up the acidic proton, because the chemical reactivity depending upon the acidic proton is responsible for the chemical activity or chemical reactivity of that particular organic compound, and therefore before the hydrolysis here, as far as the dialkylation is concerned, first use the second molecule of the sodium ethoxide, which is a base. Still there is a one proton, methylene proton, which is highly acidic in nature. So this base will pick up that proton, not the other one, and therefore you will get here CH3, C double bond O, C minus, then C double bond O, ET, and here CH2, C2 and Br, like this. And now once this carbanion is formed, then second process is known as a dialkylation here. Second alkylation, this is going to attack over there CH2, and there is a departure of Br, and you will get here this one CH3, C double bond O, then C, then here CH2 and one more CH2 here, then C double bond O, then OET. 3 CH2 I am showing. So this is nothing but a cyclobutanone type of the species we have obtained over here. Now then do the hydrolysis. H2O in presence of H plus. This is known as hydrolysis. Hydrolysis convert this ester group into as a acid, and you will be getting here CH3, C double bond O, then this I am showing this CH2, here CH2 and one more CH2 here, and C double bond O and H. After that you know that this is heating process where there is a evolution of carbon dioxide taking place, and this process is known as a decarboxylation. After the decarboxylation, how decarboxylation takes place over here? This sigma bond forming as a double bond over there, this double bond retain on it, and then this bond is breaking heterolytically and we are getting the species CH3, C double bond O, then CH. I can write this. This is a, in short I am writing as a cyclobutane structure like this, and not this. Here is a negative charge, and then there will be a protonation, H2O in presence of H plus, and finally you will end up with CH3, C double bond O. This is a cyclobutanone structure, and which is our target molecule or the final product. So in this way we can prepare this compound by using this process. This is one of the application. Now let us move on to the next one. Next, let us see synthesis of. Next one is application number 9 over here. And now let us see the application number 9. And what is that? Let me clean the board first. Here, that is a gamma diketone, we can call it gamma diketone. So let's see here. As usual, what is the first requirement, or what we need first? You need to draw the correct structure of the gamma diketones. So here, let me draw that structure. CH3, C double bond O, then CH2, CH2, C double bond O, and CH3. This will be the structure of gamma diketone. This is a carbonyl group. Adjacent carbon atom generally termed as alpha. This one is a beta, and this one is called as a gamma, delta, omega, epsilon, and so on. So this is a usual way of numbering those carbon atom adjacent to the carbonyl group, or halide group, or amine group, you can call it. Now next step required is a planning. So there must be proper planning. Then and then you can achieve your desired target. So in the planning, first point, normally we are generally here H I am writing like this and marking this part of the organic molecule. And now this part CH, C double bond O, CS3, this part is coming from ethyl acetoacetate or acetoacetic ester or beta keto ester. Ethyl acetoacetate or acetoacetic ester or beta keto ester. Second point which we are mentioning over here, this one. Another part, this part, if you see this part carefully, which I have marked here or highlighted here, which is this one, CH2, C double bond O, CS3. This part of the organic molecule, this part is coming from alpha haloketones, that is Br, CH2, C double bond O, and CS3. Look at this. CH2, C double bond O, CS3. This part is coming from alpha haloketones, that is Br, CH2, C double bond O, CS3. And now the next step, as usual, is a synthesis. Do the synthesis over here. After the synthesis, what we required? We required as a starting material, and the starting material is already given to us. Ethyl acetoacetate, everyone knows the structure of ethyl acetoacetate, CH3, C double bond O, then CH2, C double bond O, ET. And first step, normally we are using the reagent NaOET, sodium ethoxide. It is a base catalyzed reaction. Base will abstract the highly acidic proton and form the carbanion, and that carbanion is well stabilized due to the resonance CH minus, C double bond O, OET. And now I am here making as a that carbanion over here, CH3, C double bond O, CH minus, then C double bond O, OET. When this carbanion forms, it can attack on Br, CH2, C double bond O, CH3. This is alpha bromo ketone or acetone. This negative charge will pick up, attack on that Br, CH2, which is electrophilic in nature, and that reaction is a nucleophilic substitution reaction. Br depart from here, and you will get the structure CH3, C double bond O, then CH, then CH2, C double bond O, CH3, and finally C double bond O, OET. This is the part which we are getting over here. And now after that, what do you get? Here is hydrolyze it. It is a usual process, usual steps. Generally we are discussing over here. Just use it. What is that? Hydrolysis H2O in presence of H plus. This process is known as a hydrolysis. And after the hydrolysis, what is happen? The ester group get converted into acid. That's it. And you can end up this molecules CH3, C double bond O, CH, then CH2, C double bond O, CH3, and here C double bond O, then OH. Once you get the acid, and if you just heat it, there will be a elimination of carbon dioxide, and this process is known as a decarboxylation. And once decarboxylation is carried out, you will end up with the product which we are going to get here, CH3, then C double bond O, CH minus, then CH2, then C double bond O, CH3. Once you got this, then there will be another process which is known as a protonation. And protonation, during the workup, this carbanion can pick up the proton from here, and you will get the final product C double bond O, CH2, CH2, and C double bond O, CH3, which is alpha, beta, and gamma. This is nothing but our starting material. I think with this we have seen. In this way we can see there are number of applications are there, but here these are the enough example you are familiar. You can now able to synthesize any given target molecule by using as a ethyl acetoacetate. You practice it, you will be master in that synthesis. In our next lecture, we will discuss about the second molecule, which is also as an active methylene compound, that is diethyl malonate or the malonic ester. How it is prepared, which so that synthesis we will discuss in our next lecture. Till then, let us stop today here. Thank you.